All right, so this is all kind of a precursor to my last story, and this brings us to a story that came out this month. This is a paper that came out in a Nature Astronomy, in the Nature Astronomy journal, and it's by a team that wasn't working theoretically or using computer simulations, but they were working just observationally. They were observing a particular galaxy, and the question that they wanted to ask was, is the mass that turns into gas, or is the mass of, in the gas turned into stars in galaxies over a long period of time, meaning you can imagine a molecular cloud, and it gradually converts all the gas in that cloud into stars. And that process, based on the rates of star formation that we observe, is relatively slow. In our galaxy, we know that only a handful, a couple solar masses worth of stars are created per year, and it's similar in other galaxies. But so that process can either take a cloud and work on that same cloud for over a really long time, or as suggested by other observations, is the gas turned into stars, and then the cloud is dispersed by the stars before all the gas can be turned into stars. So in this case, the wind from stars and the supernova from stars can disrupt the cloud before all that mass can be turned into stars. And so in that latter case, what you have to have is you have to have multiple generations of clouds, meaning the clouds have to reform to form stars, and then they only form a few stars before they're blown up again. And so this was a paper that their observations was designed to answer these questions. And the way they did this was to observe in the radio. They used the Atacama Millimeter Array, the Large Millimeter Array, or ALMA. This is a set of radio telescopes down in Chile. And because they can be spread out over a large distance, they can create a telescope that has an extremely fine resolution. And normally in radio astronomy, the radio waves are very long, and so that means you have very coarse resolution, but by building in an interferometer, you can have very detailed resolution of your galaxy. And in this case, the radio telescopes were important for observing the gas. So the code dark gas that traces the molecular clouds, the gas often has carbon monoxide in it. So for every molecule of hydrogen, or for every 100,000 molecules of hydrogen, there might be a single molecule of carbon monoxide. And by tracing that carbon monoxide, we can trace the molecular hydrogen in the gas. And then they've also observed at another telescope down in Chile, a 2.2 meter telescope, and they observed in the optical with this telescope. And what they did was they looked at this galaxy, NGC 300, and this is another spiral galaxy, so you can see the spiral arms. It makes it look like a pinwheel. And in addition to all the stars, if you look really carefully, you can see these hints of red all along here. And those are the regions, like before that we saw, where intense star formation is taking place. So these are regions where many thousands of stars are forming. The massive stars are basically glowing really brightly, and they're ionizing all the gas and creating these red bubbles all along the galaxy. And so normally, if you looked at this galaxy with a regular radio telescope, you would just tell that there's lots of molecular gas everywhere. And so you would say that the molecular gas, the gas clouds, seem to be coincident with these bright star-forming regions. And so, but part of the problem is that normal radio telescopes don't have enough resolution to really pinpoint where the gas clouds are. So in this case, they were able to look at the gas clouds at sufficiently enough detail, along with the light emission from the stars that are ionizing the gas. So along the bottom is the light from the ionized gas. So this is the light coming from those massive star-forming regions. And then up here is the radio emission from the dark clouds. from the colder gas. And so this is this picture here shows you the highest resolution of the radio observations as well as the optical observations showing where the star formation is taking place. And then what they did was to increasingly blur their observations. So you can see that as you blur these high resolution observations, you can imagine what this galaxy would look like if you had a radio telescope that didn't see as much detail. So over here, you would know that there's CO or carbon monoxide throughout the galaxy, but you couldn't really tell where exactly it was. And over here, you could sort of tell that these clumps of carbon monoxide and the cold gas kind of lay along the spiral arms, but you really needed to come to the highest resolution observations to see whether these two were actually coincident, meaning they actually matched up. And then this particular plot in their paper shows that they don't match up. So this is, I'm going to try and explain this, but again, the blue here is from the cold gas. So this is from the gas that's emitting the radio waves. And then the red represents the star forming regions where the massive stars have erupted out of the molecular clouds, and they're, some of them might have gone supernova, but they're basically ionizing the gas around them to create these bright red bubbles. And what they see is that when they look at the highest resolution, so this is this scale along the bottom represents the resolution, where you're seeing the highest resolution on the left, and then on the right you're seeing lower and lower fuzzed up resolution. And what they see is that there's a separation between the cold gas versus the hot ionized gas at the highest resolution scales. And as they go to fuzzier and fuzzier lower resolutions, the objects basically merge together. And so this is a brilliant show of how if you observe at the correct resolution, you can see these things are not on top of each other, but they're separate. But when you go to a lower resolution, if you don't have as good of a telescope, you can't really separate them, and you can't answer this question. So what they figured out is that indeed these regions are well separated enough that it shows that, at least for this galaxy, it seems like molecular clouds will convert maybe 2 or 3% of their mass into stars, but those stars will completely disrupt the molecular gas. And so by the time you see those stars in one of these red blisters, they're completely separate from the clouds because they've disrupted the clouds that they were born out of. And this is a really terrific paper because it just shows so clearly how the cold cloud gas and the hot ionized gas are separated in space.